Don't forget to subscribe and ring that bell.
Yeah, man. We are back, man. We are going to start another wonderful journey down the 2013 AP Calculus AB practice exam that College Board lovingly gave to us. We're going to start with Section 1, Part A, which will cover multiple choice numbers in this video, 1 through 10. And we don't get no stinking calculator. I don't need no calculator anyway. I'm that good. All right, let's start these problems. Let's get going. Number 1 states that the limits as x approaches 2 of x squared plus x minus 6 over x squared minus 4 is. All right, the easiest way is to plug our x value into all of our x's. Okay, if I do that, if I take the limit as x approaches 2, that means I want every x to be 2. So this is x, which is 2, squared, plus another x, which is 2, minus 6, all over this x, which is 2, squared, minus 4. I get 4 plus 2 is 6, minus 6, 0, over. Don't start picking this one just because the numerator is 0. Okay, don't select B yet. Maybe that's the answer. We'll see. But the bottom is 4 minus, the bottom is 0 over 0. So it doesn't work. The top can be 0. That's okay. But the bottom, she's not okay. We cry. Okay, so we can't have a denominator of 0. There are really 2 ways to do this. All right, we can factor the top and bottom, or we can use L'Hopital's rule, which means we take the derivative of the top separately, then we take the derivative of the bottom separately, and then try and plug our number back in. That only applies if we get 0 over 0. Now, I will show you both ways. Okay, I don't normally do that here. So let's break this up, and we'll start on the right side. Ooh, L'Hopital's. I don't know if there's an E there. Rule. My bad. I ain't no speller of good things. So what I have here is I'm going to take the derivative of the top separately. I'm not going to take the derivative of the whole fraction using the quotient rule. Okay? Just the top. So the derivative of the top. The derivative of x squared is 2x. The derivative of my x is 1, so plus 1. And the derivative of a constant is 0. Okay? So I don't need to do anything else. The derivative of the bottom, x squared, again, that's 2x. And then we got the derivative of a constant, it goes bye-bye. Now I can try and throw my 2 in. All right? Now I can definitely try and throw my 2 in. And guess what? If I happen to get 0 out of 0 again, I do L'Hopital's rule again to this. Okay? So you just keep on doing it over and over again until you get an answer. But let's see what we get when we throw a 2 in. I get 2 times 2 plus 1 for the numerator, which is 5. And then I get 2 times 2, which is 4. Okay, so this is our answer, 5 over 4. And that is choice D. But I said I would do this. I would show you both ways. Let's do the factoring method, okay? Because as I tell my students in Algebra 2 and in Pre-Calc and in Calculus, factoring never goes away. So what I'm going to do now is I'm going to look at my limit, and I'm going to factor the top. Yeah, there you go, the top. And I need 2 numbers that multiply to -6 that add to +1. Okay, so that's going to be x plus 3 times x minus 2. Okay, all over. The bottom here is what we call a DOPS. It's a difference of perfect squares. That's x plus 2 times x minus 2. Can I reduce or cancel anything? Absolutely. X minus 2 and x minus 2 bye-bye. So now I just have x plus 3 over x plus 2. All right, again, I want this at an x value of 2. That has not changed. So 2 plus 3 gives me my 5. 2 plus 2 on the bottom gives me my 4. So I get the same answer. Okay, we're good. So I guess just pick your poison. Do I like factoring? Yay, it's so easy. Or am I like, I am a snooty calculus dude, and I am going to just do L'Hopital's rule. I don't know, I'm speaking French. It just sounds like a French name to me. Okay, either way, you get the right answer. Now, I like doing L'Hopital's rule because it makes us practice derivatives, okay, which is what you need to know for calculus. It's the foundation for calculus. But factoring never goes away. Practicing factoring is not a bad thing at all. All right? Number 2, it's a basic problem here. If f of x equals x cubed minus x squared plus x minus 1, then f prime of 2 is. They are just asking us for the derivative of f at x equals 2. So let's first find the derivative of f. The derivative of x cubed, 3x squared, minus the derivative of x squared is 2x, plus the derivative of x is 1, and the derivative of a constant is 0, so that's going to go bye-bye. Bye-bye. I want this at x value of 2. So let's find f prime of 2. 3 times 2 squared. Well, 2 squared is 4 times 3 gives us 12. Minus 2 times 2, well, that's 4, plus my 1. So it's 8 plus 1, 9. I mean, we don't get a calculator. It's not going to be anything too strenuous. B. And there we go, kids. Number 3. Which of the following definite integrals below, a, b, c, d, or e, has the same value as the integral from 0 to 4 of x times e to the x squared dx? Okay, so first things first here, kids. I'm the realist. Yeah, I get it. X e to the x squared dx. Okay, this is what I have. We're going to use u substitution for 2 reasons. I can pick it up right away if you can't. All right, because there is a function within our integrand here, and the variable portion of its derivative, meaning the non-constant, is also there. All right, and I'll explain that in a second. The second reason is all my answers have a u du in there. You're going to have to use u substitution. So when I say in my integrand, whatever function that I'm taking the integral of, that there is a function there, x squared. The derivative of x squared is what? It's 2x dx. Okay, so I know that I can get rid of that x dx by taking the derivative of x squared. There will still be a 2. I can manipulate that, and that's a constant. I can just pull constants out of my integral. Let's go. Let's go. Now we're still on here. So if u is x squared, all right, the derivative of that is 2x dx. Now, look it. I only want an x dx, okay? So when I say that the derivative of my function, the variable part of the derivative is there. The constant I don't care so much about because I can move that out of the way. But I want x dx alone because that's what I'm substituting out, x dx. So I'm going to multiply both sides by 1/2. This gets rid of this. And what I do to one side, I do to the other. So in for x dx is going to be 1/2 du. So let's start to write this. du, 1/2 is a constant. I will pull that out. All right? So both of these go bye-bye, and in for them is a du. The 1/2, which is outside, so 1/2 du. Now, x squared goes bye-bye because in for x squared, we're going to put our u. So it's e to the u. All right? But there's one thing I'm missing here. My bounds. Okay? These are currently x equals 4 and x equals 0. How do I know? I'm using x's. Okay, I'm using x's. I want them now to be in u form. The one thing that's going to convert any x to any u is this right here. Okay? So I'm going to go ahead and use that. When x is 4, my upper bound, okay, well, what happens when I throw a 4 into this x? Well, that's 4 squared, which is 16. That is my upper bound in terms of u. Okay? What about my lower bound? My lower bound is 0, right? So when x is 0 and I plug a 0 in here to square it, I still get 0, so my lower bound remains 0. This is the equivalent in u form of what they gave us. That is choice B. And look what they do. First of all, the 2's, you know, it can't be the 2's because we need the 1/2. But look what they do, and they leave the bounds in terms of x's here. That is one of the biggest mistakes that students make. They forget to convert the bounds, and they list it there before. That's the first thing you see. So make sure you know what you're doing, and make sure you convert those bounds. Okay, we had a nice run with problems 1 through 3. Now we're going to do a little bit of work, which is fine because it's non-calculator, easy work. Which of the following is the equation of a line tangent to the graph of x squared minus 3xy equals 10 at the point where x is 1 and y is -3? Two things. Equation of a line means y minus y1 equals slope or derivative times x minus x1. All right? This is my x1 and y1. So let's just put those in right now. So we got y minus my y1, which is -3, equals, I don't know what the slope is, times x minus my x-coordinate, which is 1. Now, what happens when I subtract a negative? It turns to a positive. So I've got y plus 3 equals some slope times x minus 1. Look at all of our answers. Plus 3. These are all plus 3s. Okay? Look at this. -1. These are all -1s. So guess what they're really testing us on? All of these are different. Derivative, as we stated earlier, is where I get my slope. Okay? So this question is really just testing you on taking the derivative of this. All right, so the first thing was the equation of a line. The second thing is when I take the derivative of that, I'm going to do it implicitly. I've got to take the derivatives of x's, of y's, of constants. I suppose you can try and get the y alone and then take the derivative that way, but yeah, this isn't going to be bad. Let's do it. All right, so first, the derivative of x squared, well, that's just 2x. All right? Now, I've got to do the product rule. -3x is my first term times y. That's my second term. So when I do this product rule, my first term is going to be -3x, and my second term is going to be y. All right? And we'll do that. Let's do that in green. Why not? So it's the first term, -3x, times the derivative of the second. The derivative of y, just like the derivative of x, is 1. But anytime I take the derivative of a y, I need to put dy dx. So it's 1 dy dx. We don't have to write the 1. So it's first times derivative of the second plus the second y times the derivative of the first. The derivative of -3x is -3. Equals, don't forget, I still need to do the derivative of the right side. The derivative of any constant, 0. Now, I need to find the derivative, right? The derivative is going to give my slope. This is the derivative. So I want to isolate. I want this to be alone. I want this dy dx equals. And that's how I'm going to find my derivative. So let's go back here. Let's make this. Let's multiply these out. So this is going to actually turn into -3y. All right? So let's keep our -3x dy dx on one side. -3x dy dx. equals. So I've got to subtract 2x from this side, subtract 2x from this side, and then I'm going to have to add 3y. It gets rid of this, and add 3y. So I've got minus 2x plus 3y. Last thing I got to do to get this alone is just divide by negative 3x. Divide by negative 3x. Bye-bye. Bye-bye. That's my derivative, also caringly known as our slope. I need a number. What do I plug in for x and y? I don't know. They gave us a coordinate. Why don't we plug 1 in for our x's? Boom, boom. And let's plug a negative 3 in for my y. Let's see what we get. All right, so I've got negative 2 times my x, which is 1, plus 3 times my y, which is negative 3, all over negative 3 times x, which is 1. All right, almost done. Told you we were going to do a little bit of work here. 1 through 3, those were cakewalks. Negative 2 minus 9 over negative 3. Negative 11 over negative 3. The negatives cancel. 11 thirds. That's my slope. 11 thirds is my slope. People, I'm saying it. It's 11 thirds. I'm calling it right there. TOD for this problem. Time of death of this problem. We're done. It's over. Hope he had his affairs in order because we got him. Is it E? Oh yeah, it's E. Man, that would have been embarrassing if I had just did that whole time of death thing and I was wrong. Yeah, that would. Okay, let's go on to number 5, shall we? Number 5 reads, if g is the function given by g of x is 1/3 x cubed plus 3/2 x squared minus 70x plus 5, and which of the following intervals is g decreasing? Oh, if g is decreasing, that means it's got a downward slope, which means if the slope is negative, the derivative is negative because derivative and slope are the same things. Okay, so we need to find where the derivative is negative, and I'm going to use a number line for that. But in order to do that, I need to find where the derivative is not negative or not positive, where the derivative is equal to 0. So I need to find my critical points, and then I'm going to check everywhere that is not a critical point, because if it's not a critical point, it has to either be positive or negative, if that makes sense. All right, so first off, before we do anything, let's find the derivative of g. All right, do this here. My 3 comes down. It's 3 times 1/3 x squared. Okay. Plus, my 2 is going to come down here. So I got 2 times 3/2 x minus, the derivative of this is 70. And, oh boy, the derivative of a constant goes away. So I'm going to clean this up a little bit. This is nice because the 3's cancel, and I end up with just x squared. Okay, the 2's cancel, so I end up with plus 3x minus 70. This is my derivative. Okay, timeout. The first problem we did. Okay, let's go back. Oh, let's reminisce. Back in the day, remember this was great. Remember how we did this 2 different ways? Okay, L'Hopital's rule is good because we practice derivatives. Where do we practice derivatives? I don't know. We had to take the derivative here, the very next problem. Okay, but then I said factoring is good because it really never goes away. Let's fast forward back to our current problem, which is 5. If I want to solve for this, set it equal to 0 without a calculator, without graphing it and looking at the x-intercepts, I've got to factor this. Ho, ho, ho. 2 numbers that multiply to be negative 70, that add to positive 3. I got y'all. It's a positive 10 and a negative 7. Okay, but now I need to solve for this. I T-bone that. That's what I call that. If x plus 10 is 0, if I subtract 10 from both sides, x is negative 10. That's one of my critical points. It's one of the points that makes the first derivative 0. And if I take x minus 7, set that equal to 0, I add 7 to both sides, x equals a positive 7. Again, critical point. It makes my derivative equal to 0. Number line time. So what I'm going to do right now is I'm going to create this little number line. All right? And on the top half of that, this is my derivative of g, or my slope. And the bottom half of that is my x value. I know that when x is negative 10 and when x is 7, that my derivative, they're zeros. Okay? So I'm just going to check points in the 3 kind of intervals that are split up by negative 10 and 7. What do I mean? I'm going to check a number on the line here somewhere. I'm going to check a number on the line here somewhere. And I'm going to check a number on the line here somewhere. Those 3 spots. And I want to see if that makes my derivative negative or positive. All right? It's just that simple. Let's pick right here. Love using 0 whenever I can. I'm going to put a 0 into the derivative right here for my x value. If I put a 0 in for this x squared, it's 0. If I put a 0 in for this x, it's 0. And then I have my minus 70. So 0 plus 0 minus 70, I get a negative 70. Okay, I don't care about the 70. I just care about the sign. The derivative in this interval will be negative values. Negative values. Okay? Let's pick another number on the right side. Let's pick the number 8. Okay? Now I'm going to use this here, that factored in the orange marker. If I throw an 8 into this x, 8 plus 10 is 18 in that first parenthesis. That's a positive 18. If I throw an 8 in here, 8 minus 7 is 1, positive 1. Again, I don't care about the numbers in this case. A positive times a positive will still give me a positive. So everything on the right side will have a positive slope. Okay? Which means the graph of g will be increasing here. I don't want that. I want it here where it's decreasing. All right, well, let's check the last interval. Let's pick a number less than negative 10, negative 11. And again, I'm going to use the factored version. If I throw a negative 11 in for this x, negative 11 plus 10 is negative 1 in that first parenthesis, times. If I throw a negative 11 here, negative 11 minus 7 is negative 18. That's cool that I have 2 negatives, but when I multiply them together, it would give me a positive value, which means these here are all positive slopes, so it'll be going upward. There is only one section where my function g is decreasing. That's here, from negative 10 to 7. Negative 10 to 7. Answer, D. D is for done, and we are done with problem 5. Number 6. It's a simple integral, but I don't like it for a reason, and I will show you why as we're working this out. Okay? Integrate from 2 to 4 dx over 5 minus 3x. Well, let's I don't know, let's just rewrite that. So we got 2 to 4. We'll put a dx off to the side. So it's really 1 over 5 minus 3x. To me, that screams natural log, but let's u sub, because it would really be a lot easier if I was integrating 1 over u. Okay, so I'm going to make u 5 minus 3x. That means du would be negative 3 dx, but I only have a dx to sub in for, so I want to keep my dx here and get rid of the negative 3. Let's multiply by negative third. These cancel. Multiply this by negative 1/3. And in for my dx, I'm going to put negative 1/3 du. Here's a du. I'm going to put a negative 1/3 on the outside. All right, there we go. Last thing, we need to convert the bounds. We already did a problem like this. My upper bound is 4, my lower bound is 2, but they are in terms of x. I want them in terms of u. This right here will help us convert any x into a u. For example, the upper bound, wow, that's weird. X equals 4. If I put a 4 in here, that's 5 minus 3 times 4, which is 5 minus 12. It's negative 7. It's my upper bound. My lower bound is x equals 2. So if I throw a 2 in here, I get 5 minus 3 times 2, which is 5 minus 6, which is negative 1. Aha. Gaha. This is what I don't like about this problem. Okay? Fight the urge and say, oh, negative 1 is bigger than negative 7. I'm going to switch the bounds on my integral, and then I can negate the whole thing, and then my 1/3 is going to be a negation of negative 1/3, which makes it positive. That answer won't be here unless you manipulate the log and whatever, which makes it a little bit more complicated. Keep things the way they are, and let's just integrate this right here the way we have it. Yes, I know the upper bound is smaller than the lower bound, and we are trained in the brain to fix it. Okay, but when I did this problem initially and I switched it and I came up with the answer, I'm like, it's not there. Then it hit me if I only integrate it without flipping my bounds, so that the larger value is the upper bound and the lower values the lower bound, which is what you really should do. But don't do that here and it works out perfect. Okay, so that's why I don't like this, because you kind of, there are times where you need to flip it to get the right answer. You know, and I guess, you know, I don't know, they're just trying to get you to realize when you can flip it, when you don't, but I don't know. I think it's lame. Anyways, we have our negative 1/3 on the outside. The integration of 1 over u is the ln of u, but I want that. I have negative 7 to negative 1. All right? Which means I have negative 1/3 times the ln of negative 7 minus the ln of negative 1. Okay, here's where you cannot forget your rules for having 2 logs and combining them to 1, or having 1 log and expanding them to 2. Whenever I have 2 logs or natural logs, I still have my negative 1/3 on the outside. I can combine these 2 into 1 natural log, and it becomes subtraction comes division. Numerator, denominator, negative 7 over negative 1. Okay, and let's clean this up even more. I have my negative 1/3. Well, a negative divided by a negative is going to be positive, so that's really the ln of 7. And if I take the ln of 7 and multiply it times 1/3, negative, I get negative ln of 7 over 3. Okay, if you switch those, it gets weird. Obviously, these switch. Okay, I have the negative 1 on top, so I get 7, but then I got to negate it, and then you got to do some things afterward. But that answer is choice B. And there you go. So again, you got to fight that urge. If you do that, you're going to realize the answer you come up with is not there unless you do some sort of complicating things. But then you figure out, well, I'm just going to run this integral through without flipping it, and it works out perfect. All right, number 7, we're hitting that home stretch here. Let f be the function given by f of x equals x cubed minus 6x squared plus 8x minus 2. What is the instantaneous rate of change of f at x equals 3? This just means the derivative, okay, of f at x equals 3. So really just doing this. Another easy problem. Let's take the derivative of f first. Derivative of x cubed, 3x squared, minus derivative of 6x squared, 12x, plus the derivative of 8x is 8. Derivative of a constant, 0, bye-bye, gone. I want this at x equals 3. So f prime of 3, 3 times 3 squared. I'm going to put a 3 in for all these x's, and all 2 of them. But still, it's math, right? Minus 12 times 3 plus 8. 9 times 3, 27. Minus 3 times 6, 36 plus 8. All right, 27 minus 36, what is that? I don't know, give me negative 9 plus 8, negative 1. There you go. Choice C, basic. Good thing we use L'Hopital's rule, huh? And derivatives, really helps. Number 8, love the graph of v of t, which I'm assuming is velocity. But number 8 says a particle moves along a straight line. The graph of the particle's velocity, at time t is shown above. 4 t values between 0 and m inclusive. Yeah, there are not numbers. They just have these 4 values on the x-axis, and they assign them letters, okay? Where j, k, l, and m are constants. Those are numbers, okay? And the graph intersects the horizontal axis at t equals 0. So right here it touches. Okay, at t equals k, well, right here, that's my number. And at t equals m, right here. All right, okay, yeah. And has horizontal tangent lines at t equals j, so this is a horizontal tangent line. And t equals l, okay, right here, good. For what values of t is the speed of the particle decreasing? All right, there are 2 ways to do this. There's an easy way, then there's an easy way. Both are easy. Okay. First of all, in order for speed to decrease, velocity and acceleration need to be different signs. It's like multiplication. If I multiply those, I get a negative, and we consider that like speed. So our speed would be decreasing. All right? So we can do that way. Velocity, anything above the x-axis, since y is velocity. For velocity, anything above the x-axis is positive, and anything below the x-axis is negative. So on this graph, this represents positive velocity, and this represents negative velocity. Okay. Well, what about acceleration? Acceleration is the slope of velocity. Okay. So acceleration is the derivative velocity or the slope of velocity. Okay, so I'm going to do this in the black pen. Positive slope, 0 slope, negative, negative, negative. Negative, 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 negative slope, 0 slope, positive, 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 positive. All right, so the only places where these are different, positive velocity, the green marker, negative acceleration, okay, and the minus signs. So from J to K. So from J to K, it's decreasing from J to K. Okay, and then also this is a negative velocity in red with a positive acceleration. It's a plus signs. So from L to M. Okay, believe it or not, this is the easy way. It's not the easy way. All right, so from J to K and from L to M, which looks like it's choice C. From J to K, from L to M. Now let me show you the easy way, especially when you have the graph of velocity. All right, actually, let me undo this. The 2 answers, notice, is this stretch right here from J to K and this stretch right here from L to M. All right, so let me highlight those because it's going to be obvious. I highlight her from J to K and then from L to M. Those are the 2 areas where we have a decreasing speed. Isn't this the graph of velocity? Anytime my velocity is approaching of the speed of 0, okay, because remember, y is velocity. If I'm in a car and I'm going 50, if I start to approach 0 from 50, I got to put on the brakes to go 49, 48, whatever, right? Here I'm going away from the x-axis, which is 0. From this point on, aren't I going toward the x-axis or toward a speed of 0? Okay, so this is one of your from J to K. When I'm going this way, I'm leaving the x-axis. I'm going away from it. I stop, and now from this point on, I'm turning around and going back toward the x-axis. So if you have a graph of velocity, anytime you are going toward the x-axis is slowing down. And anytime your direction is taking you away from the x-axis, because that's where velocity is 0, right here is where velocity is 0. Okay, anytime I'm taking away, my speed is increasing. All right? We don't always get a graph. We can't always do it that way. But that's another way you can do it. Someone once showed me that, and I thought it was awesome. Number 9, let f be the function given by f of x, which is x minus 2 squared times x plus 3 all over x minus 2x plus 1. So for which of the following values of x is f not continuous? That means there's a hole or an asymptote or whatever. Okay? So I just need to basically look to see what makes the denominator undefined, because that would either give me a hole or a vertical asymptote. That happens when x is 2. That would make this side a 0. 0 times anything is 0. And when x is negative 1, because that would make this parenthesis a 0. We're basically T-boning and solving to see what makes the bottom equal to 0. And that's at 2 and negative 1. And that was really, really easy, because 2 and negative 1 make that whole fraction undefined, and it can't exist at those points, so it is not continuous at those points. All right, number 10, the last one in this video. A particle moves along the x-axis with velocity given by v of t, which equals 3t squared minus 4, for a time where t is greater than or equal to 0. If the particle is at position x equals 2 at time 0, what is the position of the particle at time 3? So we have velocity. We need position. So find the position of the particle at time 3. So position is x. So x of t is position. And they say x of 0 at time 0 is going to equal negative 2. So we got that. They're asking us, well, what's the position at time 3? Okay, that's the golden question they got for us right now. So what I'm going to do is I'm going to integrate velocity to get position. And I'm going to use this initial condition they give me here to solve for my unknown c. Because I don't have bounds, meaning when I integrate velocity to get position, it's 3t squared minus 4 dt. Don't forget the dummy variable. I have no bounds. I could use the bounds 3 and 0 and try and use a fundamental theorem of calculus, but then you're going to end up with some sort of cubic that you've got to factor, and it's going to be a lot of work. This is going to be a lot easier. All right? So let's go ahead and integrate this. I should end up with, if I integrate this, I should end up with t cubed minus the integration of 4 is 4t plus c, because I have no bounds. This is my position, formula for position. I am going to use this initial condition to solve for that c. Once I got the c, then I can solve for this right here. All right? So when time is 0, the output, x of t, is negative 2. All right? So when time is 0, 0 cubed minus 4 times 0 plus c, that equals my output, negative 2. All right, bye-bye, bye-bye. C is negative 2. I can take this value of negative 2 and throw it in here, and now I have the equation for position. Bam, white, purple, why not? So x of t equals t cubed minus 4t, well, t, that's a t, haha, plus, it was c, but we just figured out that c is negative 2. So now if I want x of 3, come on now. Now it's easy. 3 cubed minus 4 times 3 plus a negative 2. That's 27 minus 12, 15. Minus a 2. I don't know, what is that? 13? Is that 13? That's 13. Look at us go. And that's it. We done. We done. We done. We done. I'll see you for the second video. Questions 11 through 20? Yeah, 20. Sounds good. Sounds like a plan. Take it easy. Until then.
Don't forget to subscribe and ring that bell.